Hello everyone. In this video, I'm going to be giving a general overview of signal processing. So what's a signal? A signal is any function that conveys information. It can be a speech signal, a music signal, biomedical signals, or in electronics terms, time-varying voltages, etc. What's a system? A system is any process that produces an output signal in response to an input signal. Processing is usually done in the output of such systems. Now that is divided as time domain processing and frequency domain processing, and both have their applications. Now the signal processing has a wide variety of use cases. It can be used in communication, in robot systems, that's automatic control, and a huge deal in machine learning. Now signals can be analog or digital. Now analog signals are ones which are continuous in time and amplitude, whereas digital signals are those which are discrete in time and amplitude. Now these can be easily convertible from one to another, and the interface systems for an analog signal to digital signal conversion is known as an ADC, or an analog to digital converter. And to convert from the digital domain to the analog domain, we use something known as a DAC, which is a digital to analog converter. Let's look at certain processing systems. Now this here constitutes an analog processing system. So there's a source, our ear perceives the speech signal and our brain processes it, and the process is completely analog. Now this here constitutes a digital system of the same. So the first, we have a transducer. A transducer converts energy from one form to the other. In this case, an audio to an electrical signal, that's a voltage, time varying voltage. Now this is interfaced with an ADC, which we'll talk about, and now the ADC converts it to digital, and now we have a DSP, which is a digital signal processor. So now the DSP is used to process the signal itself, and the output of the DSP is converted to analog using a DAC, or digital to analog converter. Right, so let's get into what exactly is an ADC. So the main processes of an ADC includes sampling and quantization. So what's sampling? Sampling is reduction of a continuous time to a signal to a discrete time signal. So this is usually done using an impulse train. So now this here is a continuous time signal, and here we have an impulse train of a certain frequency. Now when we multiply the input signal with the impulse train, so we have finite entities over here, as you can see. So we are just getting the points in certain intervals. So now this makes it discrete. So what's quantization? It's discretizing the amplitude of a signal. So now the amplitude here in a discrete signal after sampling is still continuous. So what happens in quantization is we set a number of levels. In this case, it's called 3-bit quantization. So we can basically set the values. So we round up the values of the amplitude of a signal after sampling to these discrete levels from, in this case, 0 to 7. And the higher the number of bits of quantization, the more accurate it will be. So now this, we should ask the question, how do we choose Fs, that is the sampling frequency of this of the impulse train. Now Fs is called sampling frequency. And that's given by the sampling theorem, which simply states that the sampling frequency should be at least twice the highest frequency contained within the signal. So let's see what happens if the sampling frequency is indeed not twice the maximum frequency of the signal. So this is our input signal. If our input signal is a sine wave of 1 Hz, now let's take the sampling frequency to be 2 Hz. So we sample here 0.5, 1, 1.5, and so on. And now when we sample at these points, the signal can easily be reconstructed. We have enough samples. Likewise, with 3 Hz, we have enough samples to recover the original signal. But when the sampling frequency is 1.5 Hz, now this is less than 2 times the maximum frequency. So what happens? So we have samples here, but here, as we can see, we are trying to reconstruct the sine wave, but it's clearly different from the original wave. So this is called aliasing, when we sample at a frequency that is less than 2 times the maximum frequency of the input signal. So undersampling leads to aliasing. Now this again is another overview of aliasing. So we have samples here, and the black line that you see should be the original signal, but through those samples we can draw many number of signals which pass through the samples we have taken. So we can't reconstruct the original signal. We have seen what happens in the time domain. Now let's see what happens in the frequency domain while sampling. So now a multiplication in time domain is convolution in the frequency domain. Now x of f is the spectrum of the input signal x of t. And we also know that the impulse train spectrum is basically the same thing as in the frequency domain. It is as well impulse train at the intervals of fs, while in the time domain is by 1 by fs. That makes sense. Now let's denote x of s is a spectrum of x of t, and s of f is the spectrum of the impulse train. We know that when we convolve x of f with an impulse train, we get repeated samples of the same. We can clearly see now, because of this, why we need a sampling rate that is greater than 2 times the maximum frequency of the input signal, because if it's lesser than that, then there will be overlap between in this case, the triangles. So when there is overlap, what we do is we pass the sampled signal through a low pass filter. So now when that happens, if there's overlap, it's clear that some frequency terms go missing, because we can't recover them as they are aliased. Here we can clearly see what exactly happens. So when there is aliasing, there is overlap. And now when we pass it through a low pass filter, so this is in a non-aliasing case, so we clearly have the entire frequency set. So we recover only this set of frequencies after a particular set that's around the origin, as you can see. In the same case, when the aliasing part, we clearly miss out on a few frequencies. Now there are a certain set of systems which are known as LTI, or linear time invariant systems. Let's see a few properties of such LTI systems. Now delta of t, when we pass delta of t through the system, we get a function h of t, a signal h of t. Now this is known as the impulse response of the system. Now this property, it's also time invariant, and we combine the time invariancy with the homogeneity property and with the additivity. We can clearly see that with x of t, now this basically denotes signal x of t. Now that through the system gives y of t. So this indirectly means that an LTI system implies convolution. That is, when we have an input signal that's passed through the system, the output is basically a convolution of the system response, or the impulse response of the system with the signal. And also, for Bibo stability to be conserved, integral minus infinity to h of infinity, h of t dt is less than infinity. This is known as Bibo stability, bounded input, bounded output. Now a room can be considered as a real life example of a system. This here is the impulse response of a room system. Now there are 3 distinct entities: the direct sound, that is what the sound received directly from transmitter to receiver; the early reflections, which means the reflections that from the transmitter to receiver after one reflection, just one. Reverberation after is the signal that you receive after multiple reflections. This is a very good example of a real life system. Let's look at the frequency domain of a system. Any signal can be expressed as a sum of sinusoids. This basically means that complex exponentials form a basis set for all signals. Also, they are eigenfunctions of LTI systems. Let's prove this property now. So we have a y of t which can be expressed as an integral over minus infinity to infinity h of tau, which is the response, x of t minus tau d tau. Now let's this x of t be e power st. Okay. Now y of t. Now this is possible because we have seen how y of t is basically convolution of the input with the impulse response. So now y of t can be written as the integral over minus infinity to infinity h of tau e power st minus tau. Right. Now let's take e power st outside. Well, this can be summed over minus infinity to infinity h of tau e power s tau minus s tau d tau. Now this can basically be expressed as h of s times e power st. Now y of t equals this. So clearly e power st, which was our x, is an eigenfunction, because now what's an eigenfunction? H of x of t, this is nothing but y of t, is equal to lambda times x of t. So here our lambda is nothing but h of s, that's nothing but this integral over here. Right. Why are eigenfunctions important? As any input signal can be represented as a linear combination of complex exponentials, and as they are eigenfunctions of an LTI system, even the output is a linear combination of the same complex exponentials. Now this makes it really convenient to work with, and because there are a whole lot of properties which makes everything so simple to convert it to the frequency domain. Here we can see that x of t here is a linear combination of complex exponentials. Now the same thing basically applies to y of t, because the eigenfunction rule applies here too. So all we have to do is add the impulse response component and to the linear combination. Now that's the output. Now that's really convenient. So now how is frequency domain going to help? We can see here that the main frequencies involved in this lower end, they are really quite dense. Now this is basically a frequency versus time graph. Now these here include the frequency at question and its harmonics. The rest is just noise, and that's redundant, not redundant, that's not required for us. So spectral analysis helps us in identifying and ironing out the unnecessary frequency components. So this is basically, we can thus use compression in frequency domain. Now let's try and identify the note of a music signal. Now the broken vertical lines that you can see there denote one fundamental period of each instrument. Now each of that is the C note of that particular instrument, which is of 440 Hertz. So you can see the repeating pattern in each of these. Now our task is to identify and isolate this 440 Hertz note from each signal. Now how can we do that? So in the time domain, what can be done is something known as a zero crossing based method. So this basically, what we do here is we note where the signal touches the time domain axis at 0. That's basically 0 amplitude, and goes back to the 0 again at what a particular instant of time. So this time period here is marked. So this is the fundamental. Now we can see that it's clearly giving us a 440 Hertz component, same as well in the flute. But this doesn't always work, as you can see in the oboe and the human voice, because it's reaching 0, going back, and the frequency here is 1600 Hertz, because the repeating components cross 0 more than once within the fundamental. So this method has its flaws. It doesn't work for all instruments. Now let's see another method of time domain estimation. Now this is known as the we plot the histogram of all possible zero crossings. So for example, in the piano, this is one zero crossing, and this here can be considered another zero crossing. So basically an even number of zero crossings constitute one zero crossing. So now here we have 2 of them, and here 4. So we have 2 such zero crossings, and we can get peaks at the harmonics of 440. Same thing can be seen in the flute and in the oboe as well. As we can see here clearly, we have peaks at 440 Hertz and its harmonics. Likewise with human voice as well. There's another method to do this. Now this is frequency domain estimation. So we apply something known as a Hamming window and acquire a discrete spectrum of the frequency components. And now we can clearly see peaks at 440 Hertz and the harmonics of 440 Hertz for each of the instruments. But we also recognize weaker peaks in the case of oboe and the human voice. Another method for frequency analysis is known as the Sepstrom method. Now this here is analogous to the histogram of zero crossings in the time domain. So we can clearly see peaks at 440 Hertz in the harmonics, and one of the main peaks at 440 Hertz. So these two are the frequency analysis of isolation methods. Convergence of Fourier series to Fourier transforms is seen as we increase the time period of the signal. Now, as we can see in the first case, t0 equal to 2t, we get a frequency spectrum that looks like this. Now, as we bring it further away, that's t0 equal to 4t, we can clearly see the sync of the sync form of the frequency spectrum. It's coming closer and closer. t0 equal to 80, it can't even be covered in the depiction here, and we can see it's really close. So this just implies that as a signal's period tends to infinity, then the spectrum of such a signal can be considered continuous. Now when this happens, it's known as a Fourier transform. Thus Fourier transforms are defined for aperiodic signals. This cube over here that you can see gives a nice overview of CTFS, CTFT, DTFT, and DTFS, which are the most common used for frequency analysis to convert a signal from time domain to the frequency domain. Now, in the case of CTFT, the input signal x of t is continuous in time and continuous and aperiodic in time, and the Fourier and the frequency function, the frequency spectrum, is also continuous and aperiodic. In the case of CTFS, the input signal is periodic but continuous, whereas the output, that is the frequency spectrum, is discrete but aperiodic. Now DTFS and DTFT, as you can see, are defined for discrete signals. So in the case of DTFT, we deal with discrete and aperiodic signals, well, the output, that is the frequency spectrum, is continuous and periodic. In the case of DTFS, the input signal is discrete and periodic, and the output, that is the frequency spectrum, is as well discrete and periodic. There's something else known as a DFT. So DFT is used for signals which are finite in time, a finite length signal. Now there is a clear relation between DFT and DTFS. That is, the DTFS is defined as 1 by n of DFT, the DFT spectrum component. And this basically sums up whatever we have covered for today, and hope you all have enjoyed it. Thank you.